Hello everyone, and this is part 4 of warm summary on reinsurance. So, in this part, we're going to talk about estimation. Okay, so let's begin. The estimation is in this part in this chapter. What we are going to do is we're talking about MLE. Let's start from the more simple, the easier one, the reinsurer part. So let's take ourselves into a shoe of reinsurer. What reinsurer see is just a claim that excess of the retention limit. The claim that does not yet exceed the retention limit, the reinsurer have no clue of them, right? So when we estimate the parameter using the claim that reinsurer experience, we have to use the distribution of W, the distribution of reinsurer that insurer involved, right? And this is what we have done in the first part, okay? So let's see. For reinsurer, now we have this PDF of original claim X, and if you recognize, this is variable with parameter C and gamma equal to 2. Okay, our retention limit is M equal to 3. Okay, and we are given that there are 10 claims that reinsurer involved, and sigma, the sum of all claims is 8.7, and the sum of square is 92.3. So we are asked to find the maximum likelihood estimate of C. So that's nothing much, and it is okay if you don't recognize that this is variable. I will explain why. So from the first part, we can have the distribution of reinsurer claim as follow. G of W gonna be the F, the original one, of W plus the retention limit, and probability that the thing go beyond the retention limit. So it's this one, and we just substitution this one into this, right? Right, so we have 2C W plus M e to the power of negative C W plus M square over so this here, if you don't recognize that this thing is variable, you have to do the integral to find this denominator. But if you recognize, you can just have a look into a table, and it is e to the power of negative cm square. Okay, and cm square is here, right? So it will cancel out, and we can just do some algebra, and we will come up with this distribution. We substitute m equal to 3, so we have this one, and this is our distribution of reinsurer claim. Okay, so let's do the maximum likelihood. So L here is log of the likelihood function, which is, we have 10 claim, so it's 10 log 2 plus 10 log C plus sigma of log wi plus t, right? And lastly, take away c sigma of wi square plus 6 wi, right? To find the estimator, we differentiate this function with respect to c, and we got 10 over c. Take away sigma wi square plus 6 wi equal to 0, and then our c, that our estimator is 10 over sigma wi square plus 6 sigma wi, right? Which is 10 over 92.3 plus 6 times 8.7. So we have 10 over 144.5, or approximately 0.069 okay, and that's it. That's it how to be done with the reinsurer. Okay, so let's talk about the other part. What about direct insurer? Direct insurer, they have no clue on the claim that exceed the retention limit. So let's say the retention limit is 3,000. What they're gonna see in their books is 3,000, even though the claim is 100. Even though the claim is 10,000, they're gonna still see 3,000. So the way they work is the likelihood they will sum up. So let's say we have claim of x. Okay, we have x1 x2 claim, blah blah blah, 2 x m claim. Okay, and this m claim is less than the retention limit, and we have let's say xm plus 1, xm plus 2, all the way to xm plus n. So this is m claim, these have n claim, and this n claim is reported to be m. So there is n claim that greater than m, right? Greater than retention limit, so we can just see m in our book. The way it works is the likelihood function is given by, so let's say we want to estimate the parameter theta given x. We will have f x1 times f of x2 and times all the way to f of xm. And for those other n claim, we call it the censor. There was censor because we only see the part below the retention limit. The way we deal is we just calculate that probability that the claim will greater than m, and then square it to number of the claim that was censored. This is our likelihood function. So this is what we're gonna do. Okay, I will put it here, okay. In this one, we are given that we are given 1, 2, 3, 4, 5, 6, 7 claims that paid by direct insurer, and there are also 40 claims that exceed the retention limit of 3,000. Okay. We believe the distribution is exponential with parameter of lambda, so we want to estimate the MLE for lambda. Okay, so we say x follow the exponential with parameter of lambda. L of the likelihood function of the lambda given data x gonna be tau from 1 to 7 lambda e to negative lambda x I, right? And just 7 of them, because for the rest it's gonna be probability that x greater than 3000 to the power of 3. Okay, and then we have a look at the log likelihood function. We're gonna have 7 log of lambda minus lambda sigma of xi, right? And for the last one is 3 log probability that x follow gamma follow exponential with lambda is greater than 3000 is just e to the power of negative 3000 lambda, right? So we have this one. Okay, then we have 7 log lambda. Take out our lambda, we have inside sigma xi plus 9000. Okay, let's give more explanation here. So we just pull this one up here, so it comes negative 9000 lambda, and log with e cancel out, so this whole thing is minus 9000 lambda, and we have minus here, so we pull minus out, so we will have sigma x plus 9000. Clear? Okay, so now we have log likelihood function. We just differentiate. Oh, I forgot to done here. When work with MLE, we have to check if it is the maximum point. So this one is less than 0. This is maximum. Just to confirm that the one that we calculate is maximum point. Okay. So let's back to our question. So we differentiate with respect to lambda. We have 7 over lambda, take away sigma x plus 9000 equal to 0. So our estimation is 7 over sigma xi plus 9000, which is 7 over 19,287, or 0.000T63. And this is our MLE that we want. And just to confirm that this one is the maximum point of likelihood function, we differentiate one more time, and we have negative 7 over lambda square, which is always less than 0. Then we conclude that this is maximum point. Okay, and that's all about the estimation. Thank you.